People often ask me, why do I learn things that are not related to the job I'm doing? For example, I'm a full stack developer and I'm here picking up machine learning, and the answer is because I just love to learn. it, it's something that relaxes me in a sense. So with this in mind, I'll think I'm just gonna continue with our machine learning project. And if I'm not mistaken, we stopped here. Prepare the data for machine learning algorithm. This is the chapter that we stopped. So let's do it. All right, so we need to prepare for machine learning algorithm. Here it says, let's revert to the original training set and separate the target. Know that stratified train set job creates a copy of stratified train set without the column. Doesn't actually modify strat train set itself unless you place in place true. Okay, so when we prepare data for machine learning, instead of hard coding every cleaning step, like, I don't know, housing, income. I'm just dropping these out of the top of my head. PD, pandas, cut, blah 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 blah. So instead of doing this, we should actually create functions or pipelines, and this is useful because it improves reproducibility, because we can apply the exact same transformation to new data later, or if we want to test it, some data that we want to test it, we can reuse it by writing it once. We can reuse it across this project or multiple projects. It's maintainable because it's cleaner, it's modular, it's shorter. It makes debugging and experimenting easier, and it helps with deployment as well. So I could, for example, create a method here that says add features. I'm going to take my data frame, and here I could create my data frame is the copy of this data frame, and I could maybe pull all of these methods, all of these commands here, paste them. The only difference would be that instead of housing, I would have df, and then I would return it. And basically, I would get new properties, and they are usable. It's the same shtick that we have in software development, where we just write small reusable chunks of code. Okay. Okay. Before I continue, I'm just gonna glimpse over these two commands. So we are splitting our dataset into housing and housing labels. Housing is a data frame that will contain only the features or the predictors, everything except median house value. So if I print here, print housing, and I need to run all of the commands about it, because that's why we have this failing now. Execute above cells. How much time do you need? It's running. I'll leave it. No, that's it. What if I run? It's done. So if I run this, okay. So if I run this, I'm having a new data frame that only has the predictors here. And housing labels is a separate series containing the target label, just the median house value column. So if I print this guy as well, housing labels, if I print this guy as well, yeah, I'm having the median house value here. And we created a stratified train set where here we use this train test split method. Oops. The train test split method, which takes housing, our test site, and stuff like that. but that's not important right now. So two things we have here: the housing and housing labels. And why are we doing this? So we are building a supervised machine learning model, and we require inputs, basically features that we need to predict something, and we have outputs, which is the value that we want to predict. By splitting the data this way, we can train a model by creating, let's say, a model, I don't know, fit, housing, and housing labels, basically having our input features and our target outputs. And I think that's it. Oh, maybe the copy is also interesting as well. So we make a new copy to avoid uh, modifications to the original train set data frame. Now, with this in place, we can do a lot of things next, like apply transformations, use the inputs and outputs separately, avoid data leakage. For example, maybe I can just give a simple example here. So if we have data, like, again, a simplified version, we have rooms, we have allocation, and let's say a price, completely unrelated to our example. So we have for two rural, urban, I can say 200K, 300K. We want to learn how rooms and location influences price, and then make predictions for new rows that don't have a price yet. Okay, so in this example, I just need to also mention two more things. So we have predictors and labels. Predictors are features or independent variables, the input data that's used to predict something, like the data we just talked about. And labels are values that we want to predict, like house prices. Okay, so I'm just gonna close this. Now, let's continue. Data cleaning. In the book, 3 options are listed to handle the non-values. Housing, drop, not drop, and median. And we can fill it. So why do we have 3 options in order to handle non-values? And non-values are values that are not existing, or values that are empty or missing. If you remembered, one of the predictors, one of the attributes all the way above, should I want to check, I don't know which one, total bedrooms, is missing certain values. So now we need to kind of think how to handle these. And usually there are 3 strategies. We can remove rows. Basically, we drop rows with missing values, the whole row. We can remove columns, which basically means that we drop entire column, only if it's empty or irrelevant. And there is the third possibility, in which we impute values, basically filling missing values with a statistical value, like an average value, the mean, the median, or even a prediction of the model itself. So. And here are some example of methods we can use. So the drop NA method will drop rows where total bedrooms is missing. Can I select this? It's not a coding snippet, it's the markdown text. All right, so it will drop rows where total bedroom is missing. Housing.drop will drop the entire column total bedroom. And here we have the median. So I'm getting the total bedroom, I'm calculating the median of it, and then I'm using the total bedroom property to fill in the median, basically imputing missing values with the median of the column. So for each option, we'll create a copy of housing and work on that copy to avoid breaking housing. We'll also show the output of each option by filtering the. All right. Let's print the. Okay. We have the housing data frame. We check if anything is null on the x-axis. And then we find these. Let me check. Right, so this is a data frame of booleans that have the same shape of housing, and it will be true for every cell that contains none, a missing value, and it's gonna be false otherwise. So it will basically look like this. And where's my pen? Here you are. So if I have total rooms, total bedrooms, and let's say we have 2 instances, I don't know, total rooms 5, 2, 1, man. So once we run this method is null, what we will get here is basically false, false, true, and false. This just collapses each row into a single boolean. Basically, this will return true if any of the columns in that row have an and. So basically, in this case, we'll have 0 will be false because both are false. 1 will be true because it has a non value, a missing value. Now the second one, the second command, this command will filter the original housing data frame to only include rows where the value is true. Basically rows missing data, and then we take head, which will take the first 5 rows to filter a data frame. So if I print here, null rows IDX, what do I expect to happen? I expect to get just instances of true and false. Yes, this is what I expected. And I can even check null rows dx. Can I do sum? Yes. How many do I have? I need to print them. With this, we'll see how many rows actually have null data. 168. 168. And if I print housing is null and sum. With this, we'll see how many missing values each column has. The only missing values are total, is found inside total bedrooms. So housing is null, sum. Let's continue. So these are just the options. These are just the options. I think we already passed these. We have housing options 1. We are. I forgot that my tablet was What I was basically doing before I messed up. Uh, I wanted to just check, for example, how many rows have missing values, like rows idx sum. This is gonna print how many rows have missing values. And now here, this sum command will help us see how many missing values are found in each. So we have 168, and 168, all of them are bedroom related. Okay, now let's do these one by one. We are copying housing option. If I do housing option 1, what will I get? And housing option 1 sum. What have I done? What have I done? How can I increase this? How can I open this? Open this. Ah. No, not sum. Not sum, not sum. Look at this. Look at this bad boy. Okay, basically we just we created a copy of the housing data set so we don't accidentally modify the original. This will remove any row where the total bedroom columns is missing or where it's not. This subroutine, subcommand tells pandas only to look at this specific column. And in place, we are turning it directly on housing option. But why is this not working? And now here we are trying to print the first 5 rows in the new dataset, which is housing option 1 that had missing data originally. Because we calculated this from the original housing, it's still valid. But because we dropped these rows, this line should return an empty data frame. Yeah. I can also now check how many rows were removed. Original length gonna be the length of housing, and cleaned length is gonna be the length of housing option 1. And if I run this, if I print this, original length, cleaned length, how many have I removed? I should have removed 168. All right, nice. Okay, now a bit on this option. Dropping rows miss values. It's simple, it's fast. It's okay if we don't have a lot of data that's missing, but it's risky if there's a lot of, if half of the data set is missing values. Now this is really risky. So let's check the other version. Same old, same old. We are copying the housing dataset so we don't modify the original. And here we are dropping something else. We are dropping the entire column total bedrooms from the dataset. With axis equals 1, we tell pandas that we are dropping a column, not a row. Okay, in place true. Does this directly on housing option 2. And now we print it out, and I don't see any total bedroom column here too, because our dataset now has one less feature. And we do the same code that we did beforehand. we see here the same data, but the nulls are gone. These rows not only should have missing data, they should be like completely done. Now, no. Why would we do this? Again, it's quick. It's quick. We don't need to worry about imputing the missing values. It's safe relatively. We did our visual, to be honest, to be fair, our visual examinations that are possibly not statistically correct, because in the end it's just the way how humans interpret data. But visually we saw that total bedrooms is not related probably to anything else. It's not useful for prediction. It's not strongly correlated with another one. But at the same time we potentially lose useful information. And if the column was actually helpful for our model, we can witness and experience some performance drops. So where can we use this other option? Basically when too many values are missing, like half of the values. And at that case, imputation becomes unreliable. We also can't just remove only the rows, because they will need to remove like half of the rows. Yeah, maybe if we want to simplify our model, maybe when a column is not strongly correlated, or maybe it's redundant. So let's see the third option. Now, the third option, the third approach, is one of the most common and effective ways to handle missing data. And what this does is, again, we create a copy of our original dataset. So we have it in the backlogs. We don't want to mess with it while we experiment or work on other data. Then we take our total bedrooms, we calculate the median. Whoop. Why is the median used? Is because in order to avoid being skewed by outliers. That's why we picked up the median. And then, let me just remove here. Future warning, a value is trying to be set on a copy on place method. The behavior will change upon this trio. Okay, so they are clearing up the logic. I don't need this right now. Now here, we fill all the missing values in the total bedrooms columns with the median. In place true or 80 fills this guy up. And same thing here, we're trying to pull up the same null rows who now have these total bedrooms of 434, which is the median value. Now, this is a decent approach because our number of missing values is small. The column is relatively important for us. We want to preserve the dataset size. If we remove rows, we are reducing the size of our dataset. And also we are preparing our dataset for a machine learning model that cannot handle nonce. So this is really good, this is really important. Now, why median and not mean? Let me get my trusty tablet here. Let's say we have the following values. 1, 2, 3, 4, none. Now let's say we have 1,000 here. So what is the mean? The mean would be 1 plus 2 plus 3 plus 4 plus 1,000. So what's this? It's 610. It's 1,010 divided by 5. I don't want to make a mistake. 202, right? And the median is just the middle value, so it's gonna be 3. Obviously, the mean is way too high, and the median is better representing the typical value. So we'll use the median to avoid being affected by extreme outliers. All right, now. Let's talk about imputers. Now, let's talk about simple imputer. The simple imputer is a class from scikit-learn that automatically fills in missing values in our dataset using a strategy that we choose instead of writing it manually like we did above. And it's simple as writing this. We call it by invoking the constructor, and we just say, okay, the strategy is median. We can also say mean. What other strategies are available? Strategy, mean. Okay, mean is default. What else do we have? Most frequent and constant as well. So it replaces missing data so that our machine learning model can actually train and predict without crashing. And when we can use it and when we should use it is anytime our dataset contains none or missing values, and we plan to use scikit-learn models. Like there's a lot of machine learning algorithms that do not accept missing values, so we must impute them first. Okay. Separating out the numerical attributes to use the median strategy. It cannot be calculated on text attributes like quotient proximity. What's happening here? This line selects only the numeric columns from the housing data frame and stores them in a new data frame, which is the housing numbers. So if I print housing numbers, I think I should only see numeric data frames without proximity to the C. Because a lot of pre-processing steps, such as imputing missing values or scaling, only make sense for numerical data. How can we calculate the mean or median of a string column like quotient proximity? It doesn't make a lot of sense. So basically, we're just selecting types that are numerical. Okay, now we are fitting this dataset housing num into the imputer. This line of code will tell the simple imputer to analyze the dataset and learn the median values for each numeric column. And basically, it's gonna fit all the values together. The imputer is calculating what values it will use to replace the missing ones. And imagine you're filling out a form and some fields are blank. Before you start filling, you decide, oh, okay, I'll use the median value for each field. Now this line, only this line does this for us. And now if I run this line, so after calculating, this attribute will contain the median in our case, or any other value, or in any other strategy we choose for each column the imputer was trained on. So if we had, I don't know, the amount of total rooms, if we had 100, 200, if we had a NaN value, and then 300, and then total bedrooms, if we had, I don't know, 50, none, 70, and 90, once we calculate this, we would pull 270 for total, 200 for total rooms and 70 for total bedrooms. Nice, 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 nice. Okay, if I print this out, check that this is the same as manually computing the median of each attribute. Yeah. Housing num, median, values. Okay. Housing num, median. What if I print this out? Okay, so here I have a descriptive way of showing this, but with values. But with values, I show them in this array, non-descriptive values and only values. We are doing the same thing here. Okay, so this is how we actually know what are the feature names in our dataset are. Longitude, latitude, housing median age, total rooms, total bedrooms, stuff like that. What happens if I print X? I mean, this is just gonna print the imputer, right? No. What is this doing? So we see wild numbers here because we have scientific notation numbers, which NumPy uses for large or small values. So we just need to convert it to a data frame like we did here, and now we can see them more clearly. All right, let's drop some outliers here as well. Okay, and test and categorical attributes. Let's do this now. Let's see, let's talk about how we can categorize and how we can handle actually text and categorical attributes in machine learning, because most machine learning algorithms and in machine learning algorithms we have things like linear regression, decision trees, or neural networks. They cannot understand text because they only work with numbers. So we need to convert these categories into numbers in a way that makes sense for the model. And we have two common approaches. We're going to show both of them. One of them is called ordinal encoding, in which we assign an integer to each category. And the other one is called one-hot encoding, in which we create a new column for each category with binary values. But first, let's see this. So I plucked out the ocean proximity attribute to the housing category, and I printed out head. I printed out overstayed elements here. Now, let me run ordinal encoding. We import ordinal encoding from scikit-learn preprocessing. We create it, and we create a new. This is an MP array, right? Yeah, it's an NumPy array. We create an NumPy array from the housing category. If I what have I done? Okay, now if I print this, here we see, and we only plucked out. We only took 8 elements. We see each one of these is categorized in a numerical value. For example, less than 1, our ocean is a 0. Here's another one. So both of these are 0. The first one and the last one are near bay. That's a value of 3. What else? Near ocean is 4, so on, so on. Basically, we fit the encoder on the housing categories, and then we transform the categories into integers. And I think we can see, yeah, here we can see the list, the list here we can see all the categories that we have available, and the transformed values would be 0 for less 1 hour ocean, inland would be 1, island would be 2, near bay would be 3, and near ocean would be 4. Now, why can this be a problem? If the model sees these values, these categorical values numerically, it is gonna see a 0 here, a 1 here, a 2 here, 3 here, 4 here. If we had more categories, we would continue. The model, the algorithm would think that this category here, near ocean, is somehow in a hierarchical way, so to say. Let's say greater or better than this one, because this one is 0, this one is 4. Even though they are not ordered, the model assumes that they are ordered, and it's misleading unless our categories are ranked like below average, average, above average, but they are not. So we use one hot encoding, as we did here, which gives us a binary matrix. If I do here head 5, this doesn't work because it's not an array. This is this is also an array. What's the type of this array? Like housing category, 1 hot. So the type of this is something called a sparse matrix. A sparse matrix is a matrix where most values are zeros. So I can have something like this. And you can consider this a sparse matrix because one hot encodings create lots of zeros. And doing this for 10,000 rows and 100 plus categories, you're gonna get tons of zeros. So what this type actually is a way for libraries to save memory. So they store this in a compressed format where they only store where the ones are and not all the zeros. Again, this is useful for working with large databases. And we can convert it to a regular array using this command. And here we see it. So this is the shape. We have 16,000 rows, and each row has 5 elements or categories. And if we just go back and see that the first one is near bay, and near bay in this category was 0, 1, 2, 3. So I assume this is gonna be 0, 1, 2, 3. So this is the first instance. And we just remodeled the ordinal encoding into one hot encoding. So what else? Basically, that's the gist of it. One hot encoding transforms a categorical column into multiple binary columns, one for each unique category. Yeah, and each row will have exactly one hot value and the rest will be cold. Okay, let's skip this. Here we see the categories. All right, let us also go over this these snippets of code. What we've done here is that we created, in the first line, we created a small test data frame. We are creating it with two known categories from our training set, inland and nearby. And then we are using something that might be similar to one-hot encoding. Basically, we are one-hot encoding with pandas using the get dummies method. It has its own built-in one-hot encoding. So the results in this case would be ocean proximity inland would be true for the first instance, and for the second one false true inverse. Basically, just checking this. So we have our encoder already from way above, and if we run it back, if we run it on this data frame test that we have, it will transform our known test values into the same column structure as the training data. Basically, it will just maintain consistency. And what else? Same thing here. We are trying to simulate a new data set that contains categories that are not seen during training. And pandas will make its own dummy columns for these, but those won't match the training columns. Yeah. All right, I don't think this is important. What else do I have? All right, let's talk. Let's talk another concept, which is called feature scaling. Feature scaling refers to the techniques that standardize or normalize the range of independent variables or features in our data. So what does this mean? It means that many machine learning algorithms are sensitive to the scale of input features. So if one feature ranges from 1 to a 1000 and another from 0 to 1, we will have one of them. The first one will dominate in algorithms that rely on distance matrix. So if we are predicting housing prices using, we have total rooms, which can be counted in thousands, and we have median income, which ranges from 0 to 15. Without scaling, total rooms will dominate because of the large numerical values. So we need to scale this somehow. So let's talk the first snippet. First of all, what is min-max scaling or normalization? Min-max scaling transforms the data so all the values fit within a specific range. In our case, our range is -1 to 1, but the range is usually 0 to 1. But we can use any ranges we want. There's a formula that's being used for min-max scaling, and we can use it when, for example, we have a bit of a more skewed or bounded distribution. So now, once we run this snippet of code, and if we take a look now at housing num min-max scaled, it will have every feature be in the same range. I'll go back to this because I also want to understand the formula behind this. So I'm gonna go back. But what is standardization? Now standardization rescales the data so it has a mean of 0 and a standard deviation of 1. So it doesn't bound values like min-max, and it's better for Gaussian-like distributions. It preferred in algorithms like linear regression, logistic regression, SVM, and PCA. So we have standard scaler that uses the standardization algorithm. And if I run this, oh, this is amazing. Now let's mathematically understand how both min-max scaler and standard scaler work step by step. And we will use a simple example to see how scaling is done and how it affects the values. Let me just get my trusty tablet here. Now, maybe now it works. So let's say we have a column x, and x has, oops, and x has 4 values: 10, 20, 30, and 40. Now, with the min-max scaler, we have this formula in which we have x being scaled, x minus x minimum, x maximum minus x minimum, and with this we know, okay, so this is the minimum value, 40 is the maximum value, and now for each value we are gonna say, for example, for x 10, 10 minus 10 minimum is 0, we have 40 minus 10, it's 0 divided by 30, it's 0. Then for x20 we'll have something around 0.333. For x30 we'll have 0.666. Oh, and for x40 we'll have 1. Now, once we scale it, we'll have our min-max values that will be 0.0, 0.333, 0.666, and 1. Now, for the standard scaler, we have the formula x scaled is x minus me divided by rho. So this is the mean of the feature, and this is the standard deviation. How do we calculate the mean? We do 10 plus 20 plus 30 plus 40 divided by 4, and it's 25. And we can also calculate the deviation, square root of 1 over 4, because we have 4 elements, the sum of each one of them minus me squared. So this will be, I'm just gonna do one quick 1/4. and we will have 10 minus 25 squared plus 20 minus 25 squared. And let's go on, and this value would be around 11, 18. And we can scale now each of these values, and we would get x to be, if we plug in these values in this formula, we will have minus 1.34 minus 0.5 plus 0.5 and plus 1.34. Now, both of them are rescaling. Min-max scalar will rescale to a fixed range, and our fixed range goes from whatever we define, but mostly minus 1 to 1 or 0 to 1. It's really sensitive to outliers because we can have, if we do this, and if 0 to 1, we can have something like this, mostly leaning on the 1 or the 0. But the standard scalar centers the data, and it's scaled to unit variance. And the result range is whatever we create. It's less sensitive. Basically, we can use min-max scalar when we want all features in the same bounded range. Again, it depends on the algorithms used. Now let's look at this figure. Let's just glance over this. We create one row, two column figure, histogram. For the first one, we are just putting the population on the first axis. We create 50 bins, so we will most probably have 50 of these towers, so to say. Now for the second one, we also pick the population, but we apply the logarithm. And then we create a histogram on the second column, here again with 50 bins. And this is just a way to visualize the difference between them. Now, why would we use log? If we had a certain population values, without log, if we have here all of these, and if we had one that has 15,000 or 60,000, one of them would dominate the histogram. So with log, we can actually shape them much closer together, so we can see the shape of the distribution better. Let me first display the median income to see how it looks. So maybe I'd go housing, median income. List. I'm gonna create what here, histogram. I'm gonna create, let's say, 50 bins. Let's create the size of 4. Let's show it. Will this work? No idea. It works. Okay. I didn't label it or anything. I just wanted to see how it looks. So after this, what we are doing is this line of code will calculate percentiles. We will get 99 percentile values, the first percentile, the second percentile, all the way up to 99. And they will act as bin edges to split median income into 100 bins of equal size in terms of count of data, not value. was just testing something. Basically, I wanted to make sure that this line of code does what I think it does. And I think I understand it now, because these are percentile values that tell us how our data is spread out in terms of distribution. So we have this line of code, which represents value below which 25% of the incomes fail. So 2.5625 is a value below which 25 of the incomes fail. 25% of all data is below this. 50% of all data is below this value, the median value. $75 and now we can basically say that 25% of the districts have incomes, median incomes that are less than, I don't know, 2.5, basically, let's say less than 25,000 K. 50% have incomes less than 35,000 K, and 75 have incomes less than 4.47,000 K. Okay, I just wanted to make sure I understood it before I continue. So I created a bin for each income. If I go next, all right, let's do the next one. We have here this interesting piece of code. In short, it computes a similarity score between each district's housing median age and the value 35 using something called RBF, or radial basis function kernel, or the more specifically the Gaussian kernel. So what is this RBF kernel? The RBF kernel is a way to measure how similar two values are based on how close they are, and it outputs values between 0 and 1. Close values have a similarity of 1, distant values have similarity of 0. And mathematically, it would look like this. So I'm just gonna put your color. E minus gamma x minus x0 squared. X is the input value, x0 is the target value, which we can do customly. Here we put 35, and gamma is how fast similarity drops as distance increases. And why do we do this? So let's say we suspect we have houses that are built around the age of 35 years. 35-year-old neighborhoods have some unique patterns or influence on housing prices, but influence is not binary. A 34-year-old house is pretty similar, but a 70-year-old one, not really. So instead of checking the median age, if housing median age is 35, we measure how similar is housing median age to 35, which gives us a fuzzy feature useful in many machine learning models, especially linear models or neural nets. So we can do another example. This is just an example. If I have 30, 35, and 60, and if we say that gamma is 0.1, we would get the similarity values of around 0.778 for 30, 1 for 35, and 0.0019 for 60, which means that the 30-year-old home is still similar. It's still similar to the 35-year-old one, but 60 is very, very different. Can I print this? Age simil 35 at 10. Now let's talk about this whole snippet here. This whole snippet visualizes how similarly, as we already shown you, as I already shown you, how similarly to age 35, something behaves using this RBF function or algorithm. So what we have here, we generate the ages. We are creating a linear space of the median age, which is the minimum, and the maximum median age, and we create 500 bins, 500 tick marks between the youngest and the oldest house, which will give us a nice little x-axis for plotting this. And then we reshape it via this command to work with RBF kernel. We'll have two different gamma values here, 1 and 2. The difference is in the value. With 0.1 we will have a sharp peak, and only very close ages will get high similarly. But with this one, we get somewhat wider curve, which says, okay, more of these values are treated similar. Here you can see it. And then we just plot it. X label, housing median age, Y label, create the bins. And that's basically it. Here we are drawing the histogram of the housing ages. And we overlay our curves, which are these guys. So basically we just want to see, okay, how similar this house is to a 35-year-old house. Like, it's the same thing if someone likes a specific band, Metallica, and then you say, okay, do you like Metallica? You say yes or no, but how similar is this band to Metallica? And you get a score of it, which is an approach that is more flexible, so to say.